Stephen Edwards, and I'm here with Bill Mensch, who's going to talk about the genesis of the 6502, something he was very intimately involved with. And I'm going to do this by showing a series of relevant images and start off by saying, what are we looking at here, Bill?
Well, that's the center of attraction, the 6502 microprocessor that changed the world.
Definitely one of my favorites. And so broadly, this is sort of the time is 1974, 1975 when all this was happening?
Right. Yeah. 1974, we started planning our escape from Motorola. And then we ended up at Mos Technology on August 19th, 1974. Chip was introduced in September 1975.
So speaking of Motorola, I have what I believe is one of the Motorola buildings. Can you tell me a little more about this?
Yes, I think that's the Motorola building that was at Broadway and Dobson in Mesa, Arizona.
Mm-hmm.
And that's where we designed the 6800 product line, the family.
Okay. And so that's this chip here, the 6800 series.
Correct. And that one, the 6800 and the 6502, are in the American Technology at the Smithsonian. So they're side by side in the Smithsonian.
Very nice. At least two of your babies next to each other.
Correct.
That's nice.
Correct. Yeah.
So you were part of Motorola when you were designing the 6800, and some other members of your team were there as well. Is that correct?
Correct. Yeah, there were 8 of us that left Motorola, all in force. We were actually the second group of 8 people to leave Motorola. The first group went to Fairchild. We went to Mos Technology.
Oh, okay. Interesting. And so MOS, that's this, here's an MOS building, I believe.
Correct. On the second floor there, you see those windows starting from left going to right.
Mm-hmm.
The vice president of engineering, his office was on the left-hand side. There was a conference room on the next to his, and then our team offices were down the left-hand side of the building that you do not see.
Oh, okay.
Yeah, that one right there where you're pointing out, that would be the vice president's office and the conference room.
Oh, okay. Oh, neat. Sounds good. So tell me a little bit more about Mos Technologies. I think this was the management team at about that time.
Correct. They're the founders. There are 3 of the founders. I'm not sure if, I think the 3 founders were John Pavinen up in the upper left-hand corner. He was the friend of Chuck Peddle that actually closed the deal because they worked together previously at General Electric. I think Don McLaughlin is the second one down on the left. And then the third founder is Mort Jaffe. He's in the upper right-hand corner. The process engineering manager, Walt Eisenhower, is in the middle on the right. Mm-hmm. And Don Payne, instrumental in building the mask shop, which was very revolutionary in my mind. But Don Payne is in the lower right-hand corner.
So why Mos Technologies? Why not stick around at Motorola and strike lightning twice?
Well, Motorola was planning to move us to Austin, Texas, and some of us didn't want to go to Austin, Texas. Arizona is beautiful. Texas is kind of flat. And so then we're also looking at doing something revolutionary that Motorola didn't want to do. And that was do a low-cost CPU. They already had theirs, a 6800. So to do another one better than that at another place seemed like the only way to get the job done. So Mos Technology, we were fortunate because I don't think Chuck actually knew how awesome of an opportunity it was to go to MOS. He could have. I don't remember that being the case. I was quite surprised to find out this team was doing so well in calculators that could be easily translated to our microprocessor designs. And so it was that was an amazing company, very small, relatively small, and very quick turnaround time for mass and wafers. So it was, I don't know, a breath of fresh air coming from a big company like Motorola.
Well, I'm sure. But moving to MOS also involved a rather lengthy move, though, didn't it?
Well, yes and no. Uh, we we all decided to give our resignation letters and then all move on August 19th, 1974. The interesting thing is when the salary stopped at Motorola, all of our salaries started the same day at MOS. So that was a gift. Our moving expenses, uh, I didn't move my household that I remember. We just kind of moved and set up house in first an apartment, and then we bought a home later. But it was a small, uh, what would be considered a row home back there. But anyhow, but we didn't move all in the same moving company or anything like that. We kind of moved individually, but we were meant to show up there the next week. And so we showed up at the offices next week and we got to know our new company we're going to work for.
Oh, that's interesting. Uh, Valley Forge, Pennsylvania. That sounds like quite a switch from Arizona, though. Although you had some connection with that area, right?
Correct. I grew up in Bucks County on a farm, dairy farm. So
Oh,
actually, I'm going home.
mm,
So I'm the only one that's going back to where I started. And
ah,
so it was kind of fun to, I mean, this was not planned by me. Chuck is the one that selected Mos Technology. I don't even think I knew there was such a company. There was one other semiconductor company in the area, but I wasn't aware of Mos Technology when I was back there. And I guess they started. So that's a company I could have worked for if I knew they were there, but I didn't.
hmm, interesting. And so that was where the 6502 was designed, implemented, fabricated, all of that good stuff, huh?
Correct. Yeah, we designed it from the first silicon up, and so we had to bring up the NMOS depletion load process and do all the design. And it was just 1 year of very active work. And not only did we design the 6502, but we wanted to introduce two chips. One was the 6502, and then the peripheral chip, which made a two-chip controller uh, set, and that was the 6530, which has ROM, RAM, I/O, and timer, and that went with the 6502 to do various kinds of projects, control projects.
Oh, very interesting. Yeah, no, you definitely would want support chips. So let's talk about that group that crossed the country and set it on fire. I think I've got an image here that summarizes most of them.
Correct. So the two people that are in the picture that were there when we arrived, Walt Eisenhower was the process engineering manager. And so he was the brains behind the process itself. Terry Holt in the middle sitting down, he also was process and production. Uh, One of the members of the team came from Motorola. So he understood the NMOS process. Now, Motorola didn't have a depletion load process, although I did design the process control monitor that monitored all the wafers for all of the Motorola family of chips. So that process control monitor, I did have both the enhancement load uh, process control devices and also the depletion load control devices, so that I could see the comparison. And I did that so that we could at Motorola move to the depletion load process, which we knew would be a next generation process. Well, Motorola, this is another reason why we left Motorola. Motorola really didn't want us to design with the depletion load. And even though I designed the process control monitor for it, uh, they were reluctant and finally did. After 6 months of my trying to get them to run it, they did run it. So we did gain some understanding of the depletion load process before we left Motorola. And so then Terry brought some of that understanding to Mos Technology, which helped with getting the production set. Now, on the right side is the president of the founding member and president of Mos, and he was the contact person for Chuck. They worked together at various companies, GE, and then again after Mos and after Commodore, they got it hooked up again. But anyhow, going back to the team members there, next to Walt on the left is Will Mathis, and he was one of the design engineers. He was logic design and application. Then next is me. I was a semiconductor design engineer. Rod Orgel was semiconductor design engineer as well as logic. Rod and I are the key guys that actually designed the chip from an engineering standpoint. Ray Hurt is a design engineer, and he was the designer, the lead designer on the 6532 chip that was used in the Atari game system. He and I worked on the 6532, but Ray was really the key guy that would carry that. Those circuits on the 6532 were designed that used the 6530, which I was the designer of. So then next is Chuck. He was we called him the ringleader. He was also the instruction set architecture lead. He was the systems lead, marketing lead, and just overall program lead. Next was Harry Bauckham. He was a layout designer. Then Mike Janes was a layout designer. Then we have another team member that was part of the team, and that's Sid Holt. And we found her back in Princeton, and so she joined the team after we got going there. So that's the basic team. We were a fun team to work with. We were very synergistic, and we loved our time creating the 6502 together.
Looks like quite a group. I've heard many differing stories about, oh, it was the creation of one person, it was the creation of a bunch of things, it was a copy of this, it was a complete invention. So this looks like a pretty wide, pretty diverse group of folks working on this. How would you say this, the size of this team would?
Well, relative to today's standards, it's a very small team. I mean, we might have a couple hundred engineers working on an Intel processor, but these were smaller chips, smaller processors. But this is just basic minimal number of engineers and layout designers to do the project. So this is a very small team for its day. Motorola's team, now, as it turns out for the PIA, myself and one layout designer designed that in about 3 months. So actually, I was used to working on a small team, and I enjoyed the small team. I enjoyed the total control over what we were going to do. But we all knew our lanes, and we didn't get out of our lanes for the most part. Chuck, as an example, he was all over the place as far as working with the management team and working with us as design engineers, and he was always involved in various ways. But he stayed in his lane because he really wasn't a semiconductor engineer, and so therefore he just worked with Rod and Will and myself somewhat on the instruction set and what we're going to do with minimizing the circuitry so that we could have a smaller chip than the competition, lower cost than lower power, and all that. So we stayed in our lanes as far as engineers and layout designers.
Continuing this theme of trying to make things as simple as possible, I wanted to get a little bit more technical about the internal details of the 6502. So this is its perhaps infamous programming model, which seems very, very minimal, especially by my modernized and so forth. Tell me how this came about.
Okay, so as with anything these days, it's an evolution, right? And so it starts with an instruction set that was successful. So you look for successful predecessors of what you're doing. So in the case of the 6502, what came before that, Rod and I completed the Olivetti desktop CPU, which was sold by Mos Tech. It's MOSTEK out of Carlton, Texas. They were the second source. Rod and I finished the design, and then it was licensed to Mos Tech to build for Olivetti. That had some interesting features in the Olivetti chip. So Rod and I knew the Olivetti chip to get it successfully completed. And so there were things like zero page was something that was successful with the Olivetti chip. That was carried forward with the 6800. So the 6800, we're not going to show the 6800 register set today, but it had two accumulators. So it had an A and B accumulator. It had one index, 16-bit index register. So the Motorola 6800 as a predecessor to the 6502 had two 8-bit accumulators, one 16-bit index register, 16-bit program counter, an 8-bit status register. So actually, when you look at the 6800 as a stepping stone to the 6502, you'll see that we learned from the 6800 that two accumulators isn't as valuable as one accumulator and two index registers. So if you look at it that way, we actually have in 8-bit register format, we have one less 8-bit register, one less 8-bit accumulator. We have the same number of registers for index registers. And so you end up having a different structure that would actually work more effectively in programming for controllers. Now, an 8-bit stack register that's put in page 1, and we have page 0 for quick access to registers, which I call addressable register architecture. This system here builds on the experience with the earlier processors that Rod and I worked on. So we knew what was a better register set than what we had experienced earlier. So that's kind of what's going on.
That makes a lot of sense, definitely. Oh, and you mentioned specifically controllers. So at the time, the plan was not to, say, take on the PDP-11s of the world, but rather the printers and other things. Is that
correct? Yeah, and Chuck's experience with some small control systems, like he worked on a point-of-sale terminal and some of these other kinds of systems that he would see that some of his control systems that he worked on before joining Motorola, he knew what we needed to be an effective controller. Now, the 6502 and the 6530, our target competitor was not the 6800, was not the 8080. It was a 4040. So Intel had a 4040 chipset, two chips, that was selling for $29. So actually that was our target. It wasn't PCs. It wasn't these other things that it was used for. It was simply a good controller. So Chuck's idea of building a CPU for control systems was what he saw as what we were trying to accomplish. Now, when I suggested in December of 1973 that we could build a home computer out of the 6800 plus the PIA, that's another part of the story here. The PIA plus RAM and ROM, you could build a small home controller or a home computer. And the reason why I was thinking that way is because the PIA, which I designed, was to drive solenoids and other signals that would be useful in controlling a home environment. turning on lights, turning on sprinklers, turning on things like that. And also you could program it to do, low-level accounting and other things that you might find that a user might want to do. But anyhow, that was when the Hewlett-Packard 35 calculator or whatever that had some fixed functions. So you can see when I'm thinking, why don't we build something that would go into the home? Well, Chuck wasn't interested in that, and he kind of wanted me to not really talk about a home computer because in some ways I think he knew that was going to happen, but at the time he was saying we're just doing controllers. So this was what the intention was. Now, if you look fast forward from 1974, 76 to today, I'm still in the controls business. I'm still building controllers because there are a lot of controllers out there. There's probably orders of magnitude more controllers than PCs and game systems. So anyhow, I'm still a controller guy. Chuck went on to build systems.
Now let's talk about the layout of the 6502. I have here a photomicrograph of the 6502 die that came from the Visual 6502 group. I can see some big structures here. Can you take us through some of these?
Well, okay, if we start wherever we want to start, if we want to start at the top, there's what looks like a ROM, but it's really like a PLA. And so that was that would be what I call on my CMOS, I call that the minterms. So if you're looking at logic design, there's a minterms and then there's a sum of minterms. So partially decoding an instruction with the timing state. So on the left of that, facing it, the left of that is where the timing generator is. And so for the 6502, we needed three bits, which would create 8 timing states. And we only used 8 timing states, actually 7 timing states for the 6502. So like for in my 816, I have more states, so I have actually 4 bits or 16 timing states possible. Now, what happens there is you have a timing state and you have an opcode. So on the right of that is where you have the instruction register. And so you have the instruction loaded during the opcode fetch, and that is decoded partially in that ROM pattern or that PLA, which I call the minterms. Now the logic below that, until you see the middle of the chip approximately, that's the transfer gates. Right there, what you're showing, that's the instruction decode, which if you were looking at my CMOS version, that would be the sum of minterms. But in this case, we didn't use that technique. We used just logic that would then complete the decode for the timing state to control the transfer gates that are in the middle of the chip. So you see a row of gates right in the middle there above the data path. So those are active when you want to transfer, let's say, from the index register to the ALU and transfer some other signals back and forth. During each of the timing states, we know what we want to do, and how we document that is with a flow chart. So we have a flow chart. On the flow chart, it tells you what's going on in each of the timing states of every one of the 151 opcodes. So now let's talk about the data path. So if you look at, so the top of the chip has the control signals for read write. We have the clock generators, we have the interrupt inputs, we have other unique signals such as sync and what else do we have there? Well, in the upper right hand
interrupt.
Yeah, those signals I call the control bus. Okay, then we have a data bus, which is 8 bits, and we have an address bus, which is 16 bits. So on the right is the data bus. That's where all the data comes and goes from the processor. So if you're loading the opcode, it comes through the data bus. If you're loading an address and for 0 page, it would come the next cycle on the data bus. If you're loading absolute address, then you would have 3 cycles, one for the opcode, one for the low byte of the address, and one for the high byte. An important thing about the 6502 that was not carried forward from the 6800, and I'm not sure how the 8080 worked, but the Motorola design marketing group chose to have the opcode followed by the high byte of the address, which means you can't do anything with the address like load or add a index register to it. So what we did is we put the low byte of the address. Now we can add the low byte, the address, the index register to the low byte of the address for index absolute, and then the next cycle you bring in the high byte, and if you had a carry out of the low byte, you could increment the high byte of the high byte of the address. So now that means that we were looking at things that would save a cycle here and there, and that's why the 6800 was kind of a whatever. They just didn't do the right thing there. But we knew that, and so that's why the 6502 works faster than the 6800 in that case. Now, if you look at the chip, we have of course, the buffers and the latches for latching the data coming in and latching the data we're going to put out on the out on the data bus. That's right next to the pads there. And then next we have the program counter. Now, in the case of the 6800, they had both an incrementer and a decrementer on the program counter because they didn't realize that if for single byte instructions, you have to prevent the program counter from incrementing beyond the next byte. So on the 6800, it incremented and then it incremented again. So then they had to back it up, and that means they had to use a decrementer. And so what we did was we had look-ahead logic so that we knew whether we were going to have a single byte instruction so we could prevent the program counter from incrementing. That's another speed-up technique. Less transistors used because we didn't have the decrementer. So then following across, then I think we had the ALU, and then the ALU with the decimal correct. The decimal correct actually added, I don't know, 6 mils or whatever it was. It was actually more significant than the value of it, apparently, because decimal math wasn't really that necessary. However, I wasn't the one that actually chose that, but I know that it ran into problems for other things. So anyhow, then moving across, I think it might be the stack pointer next, in X and the Y register. I'm not sure which sequence it was. And then you have the low byte of the address. So you can see where you're bringing in a 0-page address, you can transfer it right across to the address bus. So that's how we reduce some of the delays in the system. And then the high byte of the address is the ones on the bottom of the chip. That's basically the data flow from right to left. Now, there's another thing. The adder is in the middle because you're going to take some things like from the program counter or from the, I don't know that we put anything from the status register, but you would have coming from the pictures right, you have some variables or some register values like program counter. And if you're going to add the index register to it, then you want to put the index register to the right. Also, when you're doing, a compare or an add or a subtract or a logical function from the data coming in from a memory, then you bring that in from the right, and you want to have the paths built into the ALU so that you can do all these operations with the number of buses that carry that information. So we had a special bus, we called it a special bus, that we had carrying the information from the index registers and stack pointer into the ALU. It's what was needed to get the job done.
This was part of your design flow somehow?
Correct. And so you saw a portion of the logic or the schematic of the microprocessors. So everything was put in a big sheet. There, you can find them online, but there's we had the top half of the schematic and the bottom half of the schematic. And so that was the floor plan for everything we wanted on the chip. So that means that Harry, Mike, and Sid took that schematic and placed the circuitry that they laid out, converting it from the logic schematic to the actual physical layers needed to build the chip. I forget how many layers we had. We had the diffusion, we had the poly gate, we had the contacts, we had the depletion mask, and we had the metal mask. And so we had, about 8 layers or so that the mask designers laid out simultaneously so that they could build the whole thing on one layout. So that layout, if you make a mistake, then of course you can erase it. But we were designing it on Mylar, which is like plastic. And so it was done on Mylar because of the temperature coefficient of the paper, and also the humidity. So if you use regular paper, it could change in size based upon the humidity and the temperature, etc. So when you want to be accurate, you need to have a stable, and sometimes they called it stabling because it was a stable medium to design your circuits on. So that CALMA system there has that thing on the left that's hanging down with the wire. I think they called that the puck. And that was where you put that on the coordinates. So every shape, it's all rectangles. We didn't do really any circles or anything like that. They're all rectangles. So a contact would be a rectangle. Each of the poly shapes would be a rectangle. Now they can go north, south, east, and west. So actually, it's all rectangular drawing, but each of the corners of the rectangles had to be entered into the system and stored on the disk. So they used a puck there that would actually be on each of the coordinates of each of the rectangle's corners. And so there's a thing up in the right-hand corner of that's where you could look up as the digitizer. So we had a person that just did digitizing. The layout designers just did the layout. The digitizer then was skilled at doing the digitizing, and they'd look up there to make sure that the coordinates were online and that he wasn't partway between boxes, etc. Now the terminal that you're seeing there has a screen on the left of it. There's 2 screens in that under that hood. I think the left screen is the bigger screen for the actual layout, showing you what you digitized. On the right screen was like a command line. And so that's the way we digitized it. But the key part was the layout, converting this logic into the actual layers. Now I should mention one of my other best layout designers I'm married to today. And she also does the extraction. So she's like, we have physician's assistants, we have nursing assistants. Well, I created engineering assistant. That means that not only does she do the layout, but she also does the netlist. And so we can do a netlist extraction, but you need to know that the netlist that's extracted these days matches up with what was intended. So she also loads the logic in and has the netlist manually created. But so this digitizing approach we actually use also for our schematics. So what's interesting, we didn't do that at the time. So all those schematics were hand-drawn and remained hand-drawn. But today we use GDS to not only capture our schematics, but also the layout.
So let's talk now about how the 6502 started to take over the world. So I have here an ad that was advertising Mos Technologies presenting at this conference called WestCon 75. And it's interesting. It seems to be talking about the 6501 more than the 6502. Can you tell me a little bit more about that and what happened at this conference, at this trade show?
Right. Okay. So one of the things that happened with what Chuck's marketing plan is we're going to steal sockets that were created for the 6800. So the 6501 was pin compatible with the 6800. That means that they're both same pin out, 40 pin package. And what happens is the Chuck's marketing plan was, because we only had a couple salespeople, Motorola had a lot more distributors. So we're going to go around and find the customers. We're going to market and just say we can plug in the 6501 into the 6800 socket. And that's how we're going to grow the business opportunity. Well, one day when we were, probably about May timeframe, I saw that, why don't we just put the clock generator on the chip? That was not what Chuck had planned. In fact, it was counterproductive because his marketing plan was to steal sockets from the 6800. All you have to do then is recode in 6502 and you're good to go. It's a better system. Everything would work out better that way. Well, Motorola didn't like that idea. And so, but luckily when Chuck came back from one of his marketing trips, I said, hey, Chuck, why don't I put the clock generator right on the chip? I actually, while he was gone, I actually had the layout designers lay it out that way. And he says, well, as long as it doesn't affect the yield. I go, no, it's going to have the same basic, it's going to be the same die size, same everything. It's going to have a few more transistors on it, maybe a dozen transistors or so. But I'll hide them under the metal. Well, as long as it doesn't affect the yield. No, it's going to be the same thing. All you have to do is have a different metal layer for the 6502. You have the 6501 metal layer and you have the 6502 metal layer. So it'll be basically you won't see a difference in the yield. Okay, so Chuck said, okay. I said, well, actually, Chuck, it's already on the chip. So that's how the 6501 is being advertised here, because the plan was to steal sockets from the Motorola 6800. So now the 6502 is also there, and so we can charge a little premium, even though the yield would be the same. We can charge a premium. So the 6501 was sold for $20, and the 6502 was sold for $25, but the cost was the same. Everything was the same, so you're actually making more money with the 6502.
And I understand this show was quite a hit with the among the people who attended, who swarmed your booth or something. I've heard all kinds of stories about this.
Yeah. So
this trade show.
Yeah. So what happens is it was at the Moscone Trade Center, and so they had a second floor, and you could look out over the exhibit area. And what you could see that day or that weekend when we were exhibiting, you'd see all these people flocking to our little booth. And we just had the smallest booth because we don't have a lot of money. So we had the small booth. Well, there was the neighboring booths, they were being overrun. And I remember there was a pachinko game set up in the booth, which would have been to the right of facing our booth. And every once in a while, somebody trying to get to the data sheets and get their card. What we do is take a card and pass it over to someone scanning the card, which was just like a credit card reader. You just imprint it, and then you'd hand it back, and we'd hand them maybe a data sheet. And so this was going on for hours, all trade show long. We're going back and forth. And what we agreed that we would trade shifts. So Rod and I might be down there doing this for a couple hours, and another crew would come in and do it for a couple hours. Well, every once in a while, somebody that was trying to get their card scanned or the data sheet would knock over the pachinko game. And of course, they were just not happy with us. But anyhow, that was one of the most amazing experiences. And for design engineers to be there on the floor with the customers, with the people interested in what we had designed, it was just like designer heaven, where this is just joyful. And so then what we'd also tell them, hey, why don't you come back to the St. Francis Hotel? We have a suite. I think it was the MacArthur suite at the St. Francis Hotel. Why don't you come over there? We got some beer. You can see us over there. And after this exhibit shuts down, we'll be set up there. Come up there, buy a chip from us, do what you want to do, but you're invited. Anyhow, it was just one of those special times, and of course Rod and I had a few beers celebrating. Yeah, it was a little family gathering there, but that's the 8 members of the team that left Motorola. I don't think Sid's there. That's interesting, isn't it?
Yeah,
So
I don't see
Sid's not there. We didn't have anybody. We didn't have anybody from the management team there. So this is our big party. This is the big celebration of after the show party and all that. You see on the left, there's Harry. Then you see next to Harry is Chuck, and then Will, and then Ray Hurt is in the back there, and then there's Mike Janes, and then there's Terry Holt, and then there's myself, and there's Rod. So I don't know why Rod and I are separated from the others, but you can see some of the relationships there. But Rod and I were really close friends, but we didn't get together socially except a couple of times. But we worked together, and he was my mentor, logic mentor. And he taught me about De Morgan's theorem and bubble matching and other things that just he was just a very special person.
That's great.
And I want to. This might be a good time for me to say it's with sadness that we lost Chuck last December 15th, uh, and also Rod in 2012, I think, 8 years ago. And Terry Holt's not into his medical condition is somewhat tenuous right now, and his daughter built something that I think will show at this at BCF West maybe, and it's a website, team6502.org, that Terry's daughter put together, which is really a wonderful tribute to Terry and the rest of the team.
What can I say? Thank you from all of us for putting together something that changed the world.
Well, you're very welcome, Stephen. And I want to thank you for inviting me to be a participant here with this Vintage Computer Festival, Federation Festival.
Yep.
It's just really special to be around people that, it's always special to be around people that enjoy your work. And I appreciate the opportunity.